Your audio. Start video. Hey, we have Ashley with us. Yeah. All right. So let's see who we've got on board here. Oh, we've got Tyler, Ryan, and Ashley so far. Good deal. Welcome to Dynamics. Did any of you have any questions for me before class starts? We got 5 minutes. Any comments or questions? I think your exam, first exam becomes available today, if I'm not mistaken, and it's due Saturday night, I think. That should give you plenty of time to work on it. And it's over chapter 12, I believe, yeah. Now next week we start on chapter 13. Probably the most important chapter in the book. It's on Newton's second law. Let's see what it says here. Yeah. See, chapter 12 was kinematics. Chapter 13 is kinetics. Here's the difference. So that's chapter 12. Chapter 13 is kinetics. Now, kinematics, that's just a fancy word for motion. And kinetics, that's a fancy word for Newton's second law. The most important equation in our course is Newton's second law, and that's what we'll be studying next week. Well, we've got 2.5 minutes before class starts. Let's see who we've got now. We've got Tyler, Ryan, and Ashley. Just the three of you. Do any of you have any comment or question? I guess not. Well, that's okay. Well, since there's a test coming up available, I guess today, due Saturday, we could go over some of the things in chapter 12. That probably wouldn't hurt us any. Probably wouldn't hurt to go over some of the important things. Oh, look, we've got Shane and Ryan and Stuart and Tyler. We got a good class here. Somebody out there say hello. I want to make sure that we're connected here. Can you hear me? Anybody?
Hello.
Hello. Who was that?
That was Stuart.
Hey, Stuart. Good deal. Oh, look, here's some more students. Shane, we got Shane and Ryan and Nicholas. Good deal. Well, any of you have any thing you want to talk about? Because if you don't, I do. I got lots of stuff to talk about. See, we've been studying chapter 12. I'm going to be through with that today. And then you're going to take that test. And then next week is we start on Newton's second law. But I think unit 2, I think we study more than just Newton's second law. Let me look and see here. Chapter 13, Newton's second law. And it looks like chapter 14 and 15. We start speeding up here. We study chapter 13, 14, and 15, I believe. Yeah. We're going to tackle 3 chapters at once here. Okay, well, that'll be fun. See, we'll do a Newton's second law, and then chapter 14 is work energy. And then chapter 15 is impulse momentum. Am I writing big enough to where you guys can read that? Yeah, I bet you can. Yeah. Okay. Well, let's get started then, shall we? All right. I'm going to give you a problem to work here, like one on your test. And let's see if you can do it. Okay, let me make a little room here. We've been studying pulleys. What if you had a pulley system like this? We'll give these names. How about A, B, and C? That sounds good. All right, we have a pulley system now. And suppose A is going down 2 meters a second. B is going down 1 meter a second. We want to find the velocity of C. Now, we've studied pulleys, and your first thing you need to do is to write the dependent motion equation. So I'm going to be quiet for a tiny bit, and I want you to write the dependent motion equation. And then we'll find the answer, and we'll find what the velocity of C is. Okay, well that's I'm giving you something to do. Do that for me. I'll give you a minute or two. Go for it. See if you can write that. Well, we need to see if anybody's got that done. Let me go to some of my wonderful students here. How about Tyler? Tyler, do you think you know the dependent motion equation on that pulley system? Earth calling Tyler. Come in, Tyler. Unmute. Well, Tyler's not going to answer me. Stuart, unmuted. Do you think you know the dependent motion equation for that pulley system? Stuart?
2VA plus VB plus VC equals 0.
2VA plus VB, is that what you said? Plus
Yes.
VC equals 0?
Yes.
Well, now let me think about this a minute here. No, I don't. Now, wait a minute, Stuart. Wait, Uga. Yeah, Stuart, I think that's right. Good going. I think that's right. Let's check it. Now there's a couple of ways I told you guys to check this. One way is you could write, see if this has got a tension, then you go around this pulley and it would have the same tension here. And since there's two tensions pulling down on this pulley, there has to be two tensions pulling up. And of course that means that this has got two tensions. And so you just simply write, you got two tensions on A, so you got 2 VA. You got one tension on B, it's 1 VB. One tension on C, that's 1 VC equals 0, and you're done. Ta-da, and you're done. And so Stuart got it right. Now there's another way to do it. Takes about 10 minutes to do it. And it's the way the book tells you to do it. If anybody wants me to do it that way, speak up now, or I'm going to skip it. I mean, this is so easy, right? But if anybody wants me to, I'm waiting. Just say, Mr. Griffin, do it the way the book says, please. Go. Well, nobody said it, so why don't we? That's the right answer. If we did it the way the book says, we would get the same answer. Now, to solve this, you got to decide on your positive directions. Why don't we just say going down is plus for anybody? Anything that moves down is plus. Anything that moves up is negative. So if A is going down 2, well, that's plus. So you'd have 2 times 2 is 4. And if B is going down 1, that's plus. So you'd add 1 to it. And then you have an equation, and you can solve for VC. Well, I get -5. How about you? I think VC is -5 meters a second. So you know what that means? It's going up. It's going up pretty fast. See, these are both going down, but C is going up. Okay, great. Now there's another thing called relative motion. Let's do those. That'd be fun. There's the relative motion of A relative to B, for example. Now, if you're going down 2 and B is going down 1, what does, if you're taking the velocity of A relative to B, well, see, B is where the observer is. This is relative to the observer at B. And so he sees A going down 1. Are you with me? This should be a 1 when you get through. Now, the equation goes like this. Algebraically, by definition, and it's really a vector equation. If you're in 2 dimensions, you can do this same, they call it the relative motion equation. You can do it in 2 and 3 dimensions even. But in this case, we don't need vectors because it's just a 1-dimensional deal. And VA is 2. And VB is 1. And so VA relative to B is 1. So if you live on B, here, let's put a little man here on B. There he is. There's that little observer guy on B there. He's looking at A, and what he sees is A is going down. See, A is going down 2, he's going down 1, but A appears to be going down 1 meter per second. Okay. Well, what about the velocity of B relative to A? What would that be? Here, let me just write you some, and then you guys can figure them up. You can also do the velocity of B relative to C, and the velocity of A relative to C. And we could do some more, but that's enough. I'm going to shut up now for a tiny minute. And I want you to find the velocity of B relative to A, B relative to C, and A relative to C. Okay? These are called relative. They're called relative velocities. All right, go ahead. I'll be quiet for a minute. Well, let me find a student to ask here. How about Shane? Hey, Shane, are you out there? Shane, can you hear me? Come in, Shane, if you can hear me. Earth calling Shane. Come in, Shane. Unmute. Say hi, say something. Shane's not going to answer me. Well, okay, Shane won't answer me. Let's try my friend William. William, you're not going to let me down, are you? Say hello, William. William, say hello. We're trying to find these relative velocities here. I'm wondering if William's got any of them. William's not going to answer me either. Well, let's go to my friend Ryan. Ryan, you're not going to let me down, are you? Speak up. Ryan.
No, I'm here.
Yeah, good deal. Now, Ryan, what did you get any of these?
Yeah, well, I have a question first.
Yeah.
And if like VB relative to C, do you leave the C as a -5?
The C is a -5. That's right.
So it would be 1 minus -5, so it'd really be 6.
Ryan, are you talking about B like Bravo relative to C relative to Charlie, Bravo relative to Charlie? Is that what you're asking?
Yes.
Okay. Well, see, Bravo is 1, and you have to subtract C, and C is a -5. You should get 6.
Yes. Okay.
You okay with 6?
Yep.
Good, good deal. Because see, if you live on C, here, let's put our little observer person here on C. There's this little person that lives there on C. It's kind of like an elevator. I don't know if you've been in a tall building where they have elevators going up and down. But if you're going up 5 and B is going down 1, then it appears that B, relative to you, is going down 6. It's really taken off. It makes sense. Ryan, what about the velocity of A relative to C?
That would be 7.
Now let me see if that's right. I don't know. Let's see now. What you do is you take the velocity of A, which is 2, and there's a minus in the equation, and you'd have to subtract, well, you have to subtract a -5. Yeah, you got it. You get 7. If you live on C, A appears to be really taking off and going down 7 meters a second. Okay, well, I'm through with that. Unless we could work it to death, but that's enough. Anybody have a comment or question on that? All right, great. That was fun. All right, let's do a different problem here. So you know you're going to have some pulleys, but maybe you understand them okay. All right, now this one, let me get a sip of water. This is a particle, and we give you the acceleration. The acceleration of this particle is it's a function of velocity. This could be, cars have these spoilers, and in fact, don't these some of these drag racing cars, don't they have a parachute that comes out at the end to slow them down? I don't go to the drag races, but I've heard of them deploying a parachute to try to slow the thing down. And see, it gives you a negative acceleration. And the acceleration, of course, depends on the, well, in that case, it would be the relative velocity, because there might be a wind blowing. And with airplanes, with airplanes, they have a wind resistance. And the faster you go, the bigger that wind resistance is, of course. Of course, that would be true with the car too. And so this equation here deals with the acceleration. It's actually a de-acceleration, isn't it? Negative acceleration means you're slowing down. So there's your acceleration. And then it says here, when t equals 0 on this problem, when t equals 0, you're at the origin, so x is 0. We're going to be on the x-axis. but you have a velocity of 2. So you are moving. And they want when t is say 3 seconds. We'll put that in brackets. S in that case would stand for seconds. See, sometimes they use S for a variable for distance. But in that case, S would stand for seconds. Well, when t is 3 seconds, they want you to find the, they want you to find the velocity. I think it's going to slow down. If you have a negative acceleration, it would slow down, wouldn't it? Find the velocity, find the acceleration, and find the position. Now, that S there would stand for position, but I tell you what, if it's on the x-axis, we'll just use x for your position. Okay. So that's the problem. How would you go about doing that problem? We have a bunch of equations that we studied. Here, let me write some for you. There's one that goes like this. There's one that goes like this. You could put an X there instead of that, in that S if you're on the x-axis. There's one that goes like this. See, that S is just a dummy variable. It could stand for X, Y, Z, or something else. And then you have these other equations. You have this one. And you have this one here. And you have this one here. You could put a delta x in for that one. Oh, that's enough. Now, how many equations do we have there? 1, 2, 3, 4. I've got 6 equations there. Now, 3 of those equations you could use, and 3 of them you can't. 3 of those equations you cannot use for this problem. Let me go to one of my wonderful students here. Hey, William, did you ever unmute? Can you talk to me, William? He's not going to talk to me. Okay, well, let's go to somebody else then. Let's see here. Hey, Ashley, unmute and say hi.
Hello.
Hi. Hey, Ashley, 3 of those equations you may not use. Which ones are the ones you can, and which ones are the ones you can't, Ashley?
You can use A equals dv dt, V
Yes.
equals ds dt,
Yes.
and A ds equals v dv.
You can use those. That's right. What about these, Ashley?
You can't use them
You can't use, why?
because they're constant acceleration equations.
Exactly. Good going, Ashley. Those are constant acceleration equations. And acceleration is not constant. Look, acceleration changes. If the velocity changes, then the acceleration changes. So these are no good. Just forget them. They're not going to help you any. I hope you all know that. Okay. Well, since I've got Ashley, she's going to help me do this problem. Ashley, pick one of these that you want, and we're going to start with it on this problem. Which one do you want, Ashley?
How about ADS equals VDV?
Yeah, let's try that. Here we go. We're going to try ADS. Only we'd probably do it in the X. Let's do it in the X direction. Equals VDV. All right. Ashley picked that one. We're going to see what we can do with it. Now let's write the value of A in. You see, A is negative 0.5 V dx. There we go. Equals V dV. Can you all follow me? I'm sure you can. I just substituted. And then see, you could integrate this. But now here's the problem. This has got a variable V. It's not a constant. V is changing. And this is integrating with respect to X. That's a major problem. You can't do that. Talk to your math teachers. They'll tell you that's a no-no. So we can't do that. Ashley, got any other ideas?
A equals dV dt.
A equals dV dt? Yeah, okay, let's try that. Great idea. Good thinking. Okay, we're going to try A is dV dt. All right. Well, let's put A in there. So we have minus 0.5 V equals dV dt. Then what do I do? Ashley, the ball's back in your ballpark. You understood from here to here, okay? But what do I do now? I mean, I could put that dt over here. Let's try that. Here we go. I'm gonna, here, I'll do it over here. I'm gonna go minus 0.5 V. I'm gonna scoot that dt over there. Equals dV. I mean, that's legal. But then what? Well, we could try integrating. Now, we have a problem. This variable V here, that's not a constant. That's a variable. But we're integrating with respect to time. And we don't have this as a function of time. So we're up a creek again. You can't do that. Your math teacher will tell you, whatever you have in here has got to be a function of time if you're going to integrate with respect to time. Did they ever, Ashley, did they ever teach you that in your calculus class?
Yes.
Yeah, of course they did. So, well, we're stuck. That didn't seem to work. Ashley, you have any other ideas?
I'm not sure.
Well, here, let me show you how to do this. What we want to do is we want to get the V's together away from those T's. So see if you can get to here with me. Put that dt off all by itself there. Come over here and divide by minus 0.5 V. Now, is that legal? Can I do that?
Yes.
Oh, yeah. Yeah, that's legal. Sure it is. And then see, you know what this amounts to? It amounts to minus 2 dv over v. Now, do I need to explain how come this here is minus 2? I'll be glad to.
No.
Nah, I don't need to explain that. All right, so now we're going to integrate. Now watch this now. We're going to integrate dt. And that minus 2 is just a constant. And then we're going to integrate. Ooh, looky here. We have dv. We're integrating with respect to v, and we got a v. We're okay now. Now here's the hard part of this problem. You got to put in the limits here. Well, see, t goes from 0 to 3. That's what they said. T goes from 0 to 3, and v goes from 2 to an unknown v. And we can integrate that. If you integrate this, you just get a t. Do I have room here? Yeah, maybe. I'm getting a t, and you have to integrate from 0 to 3. And here I'm getting a minus 2 natural log of v, and I'm integrating from 2 to v. Did that show up? Yeah, that showed up. We're almost done, and we almost have this problem licked. I just need room to finish it here. How about I make some room over here? When you integrate this, what you get is 3 minus 0, so you just get a 3. And when you integrate this, what you get is minus 2 natural log of v, net subtract, remember you have to subtract, a minus 2 natural log of 2. Can you guys get from here to here? Can you make it? Okay, you got calculators. I'm going to shut up for another minute and a half, and I want you to find v for me. See, that's part of the problem. We're supposed to find v. Look, here's an equation with only one unknown. It's possible. We took calculus in school. We can do this. I'm going to shut up, find v. You have a minute and a half. Go for it. Well, let me go to, hey, let me go to Braxton. Braxton, are you
Hello.
out there? Hello.
Yeah.
Hey, have you got this v figured out for me yet?
Yeah. I got 0.446 meters per second.
That's what I got. I got point 0.4462 meters per second for the velocity. Now, does anybody out there need my help? Braxton and I know how to do it. Anybody out there need my help to get that answer?
I got the answer, but I am actually confused on how dv over negative 0.5 v equals negative 2 dv over v.
Oh, that's Ashley again, right?
Megan.
I'm sorry, Megan. Megan's confused. How I got this?
No, how dt above that before we integrated.
Oh, how I got this?
Before we integrated, how dv over negative 0.5 v equaled negative 2 dv over v above that.
Well, when you divide by 0.5, you get 2. See, 1 divided by 0.5 is 2. You're okay on that, right?
Yeah.
And if there's a negative, well then, if that's a negative, well that makes that a negative. So you understand the negative too?
Yeah, okay, I guess I was just confused.
So now you're okay?
Yeah.
Okay. Thanks for asking. Anytime you're confused, just ask. Okay. How about the rest of you? Do I need to go through this or not? Anybody? Here's your chance. See, I just assume you can do that then. I just assume since you're quiet out there, that that's no problem. You can do that just like Braxton can do it. Am I right? Or do we have people that don't have any idea how I did that? Or Braxton did it? You have to ask. Okay, well, we got that. I'm not going to show you if you already know how to do it. I don't want to bore you out of your gourd. All right, now look, we're supposed to find the acceleration. Well, you know, we could find the acceleration. Acceleration is just minus 0.5 times v. And if that's the v, I can multiply by minus 0.5. Let me do that. Ta-da, I just got the acceleration. It's minus 0.223 meters a second squared. Yay, we just got the acceleration. We got the velocity. Now let's get the position. Now how are we going to find the position? Good question. How are we going to, here, let me make some room here and we'll find the position. I need room is what I need. I think I was talking to Ashley a little while ago and she came up with a ds or dx in this case equals v dv and we abandoned it. We said, well, never mind that. We'll try something else. But here's what you can do. Now watch this. We could write this like this. Can you get from here to here, students? Can you make it? Well, yeah, you can make it. And look, the reason I did that is I can put in for A minus 0.5 V. Okay? And you know what that's going to give me? It's going to give me a minus 2 dV. See, the V's will go bye-bye. Look at there. They'll go bye-bye. See, Ashley and I almost had that a while ago, and then we decided, no, we don't know what to do. Well, we can do this. We're going to integrate dx equals minus 2 dv. Yeah, we can do that. Now x goes from 0 to x, and v goes from 2 to v. But hey, we know what v is. Uh-oh, I erased it. Does anybody remember what we got for our answer for v? We got it, but I erased it. What was it?
0.446.
Thank you so very much. Hey, we can do this. I think I'm going to shut up for another minute, and I want you to do it. And I want you to find the position. We got it made. I know you can do this. Okay, do it. Well, let me find one of my wonderful students here. Hey, Mark. Mark, unmute and say hello. Come on, Mark. There you are.
Yeah,
Hey, Mark, were you able to get this value of x?
I believe so.
What'd you get?
3.11.
That's what I got. I got 3.108 meters. How about some uh-huhs? I want to hear some people say, yeah, they got that, or uh-huh. Go ahead.
That's what I got.
Yay, there's the three of us now. Now, does anybody need me to do that? I'll be glad to do that if you need me. Otherwise, we'll move on. I guess you don't need me. You took calculus, you ought to be able to do that. Good going there, Mark. Okay, one last thing here on this one, then we'll do some more here. Today's kind of a wrap-up day for Unit 1. See, Unit 1 is, in this course, is Chapter 12. We spent all this time on Chapter 12, but when's our next class? Monday? Next time we meet, it's going to be Chapter 13. Let me see who I owe money to now. Just a minute. I just pushed the green button, then I pushed the red button, made them go away. Probably just somebody that I owe money to. Oh, okay, yeah. Before I wanted to show you one other thing. Did you have any question on this problem? All right, let me show you one other thing here. Now you see that 0.5 there? Well, it's actually a minus 0.5. Does that 0.5 have any units? My question is it unitless? You know, there are things that are unitless. Like, for instance, the area of a circle. You guys all know and love this equation, pi r squared. Did you know that pi there is unitless? It's, what is it, 3.1415, 3.1415 Let me see what it is. 3.14159, and it goes on. I had a student one time memorize pi to 50 places. Pretty good trick there. Okay, but you know what? It's unitless. It doesn't have like meters per kilogram or anything like that. It's unitless. What about that 0.5? Does it have units? Let me go to one of my students here. And Alex, unmute Alex. What do you think? Do you think that that negative 0.5 has units? If it does, what are they? Go for it, Alex. Alex is not going to answer me. Well, Mark answered me a minute ago. Hey, Mark, what do you think? Does it, that 0.5, negative 0.5, does it have units? And if so, what are they?
1 over seconds.
Now, Mark says they're 1 over seconds. We'll put a little s for seconds. There we go. Now, I want to see if that's right. Hope you can read my writing. That's supposed to, there we go. Okay, if that's minus 0.5, 1 over seconds, and the velocity we know is meters per second. It's meters per second, yeah. Well, then you get meters per second. Yeah, that's it. Good going, Mark. I'm proud of you. When you get all through, you're going to have meters per second squared. Yeah, it's got units. That negative 0.5 definitely has units. Good going. Okay. Now I'm going to find us some more fun things to do here. Unless you have a particular comment or question, now's your chance to speak up. Otherwise, we're going to do what I want to do. Okay, I gave you your chance. Nobody said anything. Let's suppose you had a parabola. You all know how parabolas go. They kind of go like that. So suppose this parabola is you got an x and a y axis, and the parabola itself is x squared minus maybe 2 or something like that, or maybe, yeah. So see, when x is 0, you get a minus 2. That would be a minus 2 right there. Now, when y is 0, well, that doesn't work. That'd give you an x is 1.414. When y is, here, let me change this. Now let's see. If x is 0, no, wait a minute. I'm getting all mixed up here now. If x is 0, y would be minus 4. And when y is 0, x would be 2. Let me change. Let me draw the parabola better. Here we go. That'll be okay. It's more of a narrow. It's okay. It's more like that. This value is -4, and that value there is 2, isn't it? Right? See, when x is 0, y is -4, and when y is 0, x is, yeah, there you go. Okay. And here's the origin. Now let's suppose your body is right here, and it's going up. It's going up the hill. Let's put a velocity right here. Here we go. There's the velocity of your body. Now here's what I want you to do. There's your body. Now at the body, not the origin. See this right here, that's called the origin. But at the body, I want you to sketch the unit vectors. There's an I and a J. There's a tangential and normal. And there's a radial and transverse unit vectors. At the body, I want you to sketch all 6 unit vectors. There's your body, there's your path, there's the equation. I want you to sketch those. Go ahead, I'll be quiet for a minute or so. And I want you to sketch those on your paper there. And then we'll talk about it. Go for it. You should have some of those done by now. I like to put my unit vectors in green. I don't know if this will show up, but here's your I. There's your I unit vector. And it's always in the direction of your x-axis. Now here's your y unit vector. Now you don't put it over here on the y-axis. You put it right here. That's J. J is the unit vector in the direction of the y-axis at the body. So I did that. Now let's do the tangential. The tangential unit vector is in the direction of the velocity. So if this is the velocity, there is your tangential unit vector. Is that what you have on your paper, I hope? And then the normal unit vector, it's perpendicular to the velocity. Hope you can read my writing. That's supposed to be u with a little n under it. That's the normal unit vector. It's perpendicular. These are all perpendicular. I and j are perpendicular. The tangential and the normal are perpendicular. The radial and the transverse are perpendicular to each other. Okay, and then you have the radial and transverse unit vectors. Okay, well, really, to get those, you need the position vector. I never drew it, but see, it goes from the origin. There it is. That's the position vector. The position vector R. Position vector R. It goes from the origin to the body, and it turns out that the radial unit vector is in the same direction as the position vector. I have to put it on top of that I guess. Here, I'll squeeze it in here. There it is. It's in the same direction as the position vector. You know what? The I and the radial unit vectors pretty much are on top of each other. They're the same. And then the transverse, they call this, it's got a name. Let's call it the transverse unit vector. It's perpendicular and counterclockwise to the radial. So, you know what? It goes in the same, it's right on top of the J unit vector. Kind of hard to draw that. I'll cheat by drawing it up here. There's your transverse unit vector. How'd you do? Hopefully you got all those right. Now, we're going to find the angle right here. See this path? See this velocity? There's an angle right here. I'm going to call that angle, I don't know, theta might be a nice name. We want to find the angle. It's not straight up right there. Can you see that? It's pretty steep, but it's not straight up. We're going to take a minute or two, and we're going to find that angle. I'll shut up. Go ahead. Find the angle that the velocity or the path makes with the x-axis right there. Go ahead. Well, I wonder if my excellent students know how to do that. Let's see. How about Tyler? Hey, Tyler, are you with me? Answer, say hi. Tyler?
Yes, I'm here.
Yay, good. I'm glad you're here, Tyler. Tyler, do you know how to find that angle that the body makes with the x-axis? Do you know how to do that?
No, I don't.
This is your lucky
Sorry.
day, Tyler. This is your lucky day because we're going to show you how to do it.
Sounds good.
Count yourself blessed. See, you're going to learn something. The ones that already know how to do this, I'm kind of wasting their time, but I'm not wasting your time. Here's what you do. And the thing is, Tyler, you know this. You know this, that the tangent of that angle, you've studied this, is equal to dy dx. I bet you know that. See, that's called the slope. The first derivative is called the slope, and the tangent of the angle is called the slope. That's the slope. Did you ever learn that in school, Tyler?
Yes, I did.
Yeah, of course you did. Of course you did. All we got to do is take the derivative. Okay, here goes. Now, when you take the derivative, dy dx, I get 2x. The derivative of a constant is 0. And if x is 2, then you get 4. So this dy dx is equal to 4. It's equal to 4. Now get your calculator, Tyler, and put in a 4 and hit the arctangent button and tell me what you get.
The 1.325.
Now that's in radians. That's in radians,
Oh.
Tyler. That's okay, but I want it in degrees this time. Put in a 4, hit the arctangent button, but you need to be in degrees.
75.9.
That's it. That's it. 75.9 something degrees, right, Tyler?
Yes, that's correct.
Proud of you. Good going. Now, what he did before was in radians. Guys, be careful about radians and degrees. You don't want to be in the wrong mode and get the wrong answer. Okay, now here, let's do one more thing with this, and then we'll go on to more fun things. There's a radius of curvature right here. I tell you where it is. It's over here. There's a radius of curve. See, there is a curve there. Can you see it? There's a slight curve there. And we're going to find, here, let me write the equation for you. It's in the flap of your book. But when the body's right there on the x-axis, when x is 2, it's got a radius of curvature. And if you look in the flap of your book, it says this here. If you don't know what I'm talking about, go to the flap of your book. It's right there in the flap of your book where my finger is wiggling. That's the radius of curvature. I'm going to shut up for a tiny minute. And I want you to find the radius of curvature when it's right there. Go ahead, I'll give you 2 minutes. Go for it. Well, I got what I think is the radius of curvature. Let me go and let's ask, how about Shane? Hey, Shane, are you with me? Say hi, Shane, if you're with me. Unmute Shane and say hello. Well, he's just gone coffee break or something. Stuart, let's pick on Stuart again. Hey, Stuart, say hello.
Hello.
Hello. Hey, Stuart, have you figured out the radius of curvature right there when the body is on the x-axis?
I'm not sure if I got it right, but I got 35.05.
That's what I got. I bet that's right. Two of us got it. How about anybody else?
Yeah.
There's
That's what
a
I got.
yeah, we did great. Now, if you did this to scale, if this distance is 2, man, 35 is way the heck out here someplace. So there's not a whole lot of curvature there. It's kind of flat, but there is some. It has a radius of curvature. You don't. Let's put it this way. Anybody need me to put in the numbers? If you do, I will. Okay, nobody said anything. Just speak up and we'll do it. Okay, I got enough time. Maybe we can try one more problem. Did you have anything else to say before we try our last problem today here? All right. I wanted to do a problem here that I thought was interesting. It's a review problem. They have these review problems at the end of the chapter. Yeah, here we go. This is review problem 12.6. It's a football, looks like a football game there. A player kicked the football 126 feet. Okay, here he goes. He's going to kick this ball 126 feet from start to finish. Doesn't tell you how high it goes, and it doesn't tell you the angle that he kicks it at, and it doesn't tell you his initial velocity. But it observed that a player kicked the football 126 feet, and he did it in 3.6 seconds. Determine the initial speed of the ball and the angle at which it was kicked. Okay, that's our problem that we're going to figure out here. And we have 9.5 minutes, so we're going to have to speed up a little bit. Okay, well, if he goes 126 feet in 3.6 seconds, well, we could get his x component. See, that velocity there has an x component and a y component. We could call that Vx and Vy. How's that? Does that show up? Yeah, that shows up. Not very good. That green doesn't seem to show up very good. But we can figure his velocity component in the x direction. See these little things underneath, that tells you it's a component. Gives you the x. Let's get the x component of the velocity. If it goes 126 feet in 3.6 seconds, what's the x component of the velocity? You tell me. How
35
fast is
feet
he
per
going?
second.
How much?
35 feet per second.
Yes, exactly. 35 feet per second. Good going. And you know what? That's constant. That football, it goes at a constant speed in the x direction. But now the velocity in the y direction is not constant. It's slowing down. See, when it gets to here, it's smaller. It'll have a Vy. It'll have a y component. And here, it's just a tiny y component. And you know what? Right here, the y component is 0. Doesn't have any y component. And then here, it starts going down and it picks up the y component. It gets bigger and bigger. And when it quits, when it hits the ground, it should have a y component going down equal to the y component going up. So the y component changes all the time. We know the x component. See, if we only knew what that y component was, we could get this velocity. Because, see, that velocity would be the square root of the 35 squared plus that Vy, the initial Vy squared. But we don't know what it is. You got any ideas? Anybody out there? We got a smart group of students. We got 6 minutes. I bet we can figure out something. Got any ideas?
Use a constant acceleration equation.
Yeah, we get to use that. Good going. There's several. One goes like this. Let's see. V equals V0 plus AT. Now, if you're doing it in the y direction, then we know what the acceleration is. Now, this is in feet. It's English stuff. So the velocity in the y direction is equal to the initial, but see, it's minus 32.2 times the time. And here's the dirty secret. The dirty little secret is go up here to the top. The velocity in the y direction is 0 there at the top. And that's going to equal to the initial velocity in the y minus 32.2 t. But the time to get to the top is not 3.6. See, it takes 3.6 to go all the way. The time up here to the top is 1.8. That's half. So look, if you know what the time is, you could solve this and you could get the velocity. Yeah, we could get the velocity in the y direction. Go for it. We only have 4 minutes, but you got time to do it. Help me find the velocity, the initial velocity in the y direction. Okay, go for it. Wonder if that's right. I'm getting 57.96 feet per second. We think that this v sub y is, well, will that show up? 57.96. Yeah, maybe that shows up. And see, the x, we know what that is. It's 35. feet per second. So basically what we got here is we got 35 and 57.96. And what we want, we want this velocity here. We know what that is. It's 57.96. Okay? So put that in your calculators and find the initial velocity for me. Go ahead. Did you get 67.7 feet per second for the initial velocity? And so you can get the angle theta here now. It's going to be an arctangent, isn't it? Put that in your calculators and give me the angle that it's kicked at. Go ahead. I got an angle of 58.87 degrees. Now let's see how we did. Go to your answer book here. Somewhere in the back they have answers to this stuff. Let me see if I can find it. I don't know. Somewhere they have answers to review problems. Maybe you can find it. I'm having trouble. Hey, there they are. The answers to the review, they're in the back. And what we want is problem 12-6. And they said 67.7 feet per second. What did we say? Yeah, that's what we said, 67.7. Yay, we got what they got. And they said the angle is 58.9. Wait a minute. How come we got a different angle?
Oh, it's the same angle, isn't it?
They got 58.9. Oh, no, that's what we got. That's what we got. The answer book got 58.9 degrees. We're okay. Hey, we solved that problem. Now, if I had more time, and I don't, we could have more fun with this problem. We could find out where it is at different times. We could find out the what do they call the radius of curvature at different places, but we don't. We're out of time. Here's your chance, your last chance to say anything. I'm going to push this red button here unless you say something.
Maybe you covered it before I got in, but how does this exam work? What are we supposed to do for the exam?
It's basically it's an open book, a take-home exam. You're going to do it for me. You do have a time limit though, but there's no panic. You got till Saturday at midnight. You can do it.
All right.
Enjoy. It'll be fun. I think it's available already. Any other questions from anybody? All right. Well, I'll see you. I'll have those graded, I'm sure. There's homework too, and I think it's due Saturday night.
Where will the exam be available?
I think
Just
it's
on
available.
Blackboard Unit 1?
I think it's available right at this moment.
I just
Go-
see homework 7.
Yeah.
Yeah, I don't see an exam anywhere.
Well, it should be there in Unit 1 at the tail end.
I don't see it either.
Really? Okay, I'll double check on that. All right? I'll double
Okay.
check on that, but I think it's there. And enjoy. You'll find it. We'll make sure it's on there. I'll get my IT person on it if there's a problem. Okay, we're going to sign off, and I will see you on Monday.
All right, bye.
Bye-bye.
All right, thank you.
Thank you.